So welcome everybody, also those in the room, to this event of European Bioplastics. This is a side event to the main conference. My name is Chiara Bearzotti, and I'm part of the team at European Bioplastics that is looking into research and innovation projects. So I have the pleasure to have with me today a number of representatives of several successful projects that have been funded by the program Horizon 2020 and Horizon Europe through the funding of the CBE and the BBI. So if you're not familiar with these names, you will be by the end of the day, probably. We are talking about highly competitive calls for research and innovation funding, where basically there are many applicants, many consortia, and maybe one or two are funded. So this is where you got creme de la creme, actually, here invited. We got here several people invited from 3 projects that actually competed on the same call. So we're glad as European Bioplastics to be part of 2 of them. Both are forgot us in the last run. But they are all dealing with recycling technologies for bioplastics. This is a challenge that is acknowledged for those working in the industry and also recyclers as well. And the other 2 projects are a bit older because they are kind of halfway and maybe also finishing one of them next year. And they are a bit more advanced, and they've been dealing with, again, part of them in recycling technologies, but mostly about packaging, but also in treating, let's say, post-consumer waste for entering again the cycle. And it's all dealing with bioplastics, as I said. So I just wanted to make sure that we are on the same page here for the goals of today. Goals, there's just 3 basically. The main thing is give you insights about where do we stand with the latest technologies for recycling, where the plans are for these upcoming projects. Then we will present these 3 outstanding projects, Moebius, ReBiocycle, and Prosper. They will be focusing just on technologies for the next 4 years. They just started this year. And actually, we would like you to provide inputs as well on the challenges of these recycling technologies. What do you think it's possible to do it, what not? So this is where the matchmaking part will be a bit more collecting also your inputs. We have arranged here in this room different tables in different areas. So you will see that we got posters of the different projects, and we got small tables where you will be, let's say, gathering together with one of the speakers. During the matchmaking, you will be moving from table to table every 7 minutes. So this is where the speed dating is taking place. Now, I'm glad that it's a manageable audience, so that it's possible for you to talk to the speakers, and it's possible to take advantage and asking questions, and the speakers will take down the questions, and the summary will become our proceedings of this event. The agenda, as I said, we got different speakers with different talks foreseen. The first one will be Miriam Lorenzo, Moebius. Then we will have Eva and Krisa for the BioSupac project. We have the BioMac with Ronnie, ReBiocycle, Prosper. We will mix it up a little bit. This is not the final schedule, but this is where we will bring first the 3 projects, and then Ronnie will close the activities. We will have a joint Q&A at the end of the presentations, and then we will move to the speed dating. Now, these are the speakers. So just for you to remember, we will have the names also standing on the wall for the final slide, so you remember to whom you're talking to. It's easier. And yes, as just last reminder for the people online, switch off the camera, mute your microphones, so that we can make a clean recording, and we can make it also available. Last thing, you also got a notification from us about an introductory paper that was circulated to you, a PDF. It's the first link that you see on the left. This is a document that is presenting these projects. Of course, we will enhance this document. We will make a proceeding out of this. This is in our interest. And there is another paper that I would like you to have a look at. And this is the end-of-life position paper of European Bioplastics. And this was also recently revised and published on the website of the association I represent. Last thing, it's just a bit of promotion. If you're not a member, maybe you might be interested in becoming one of our members. So there is a procedure to follow, and just be in touch with one of us, one of the team here. We have several people in the room. Okay, without further ado, I give the floor to Miriam. And we can go to the next presentation. I will need our colleagues to change the slide and go to presentation number 2. Thank you very much. Thank you, Chiara, for the introduction and for giving me the opportunity to present this wonderful project. It is called Moebius. And first thing I want to do is to explain about the name because we were discussing here in the table. Yes, Moebius is trying to integrate two concepts. As you can see, the Moebius, represented by the Moebius stripe, will mean kind of infinite. And on the other hand, we have the bios or bios, and we want to integrate these bioplastics in which we are talking about today. And the mix of these two words is making probably the bioplastics, giving them an infinite life if possible. So this is the romantic part of the talk and about the short name. And yeah, for the long name, it's not so romantic. This project is called Improving Waste Management of Bio-Based Plastics and the Upcycling in the Packaging, Textile and Agriculture sector. And it is coordinated by ITENE. ITENE is a research center located in Valencia. We are devoted to packaging, transport and logistics. And yeah, I'm going to give you an overview of this project that started in last June. As you can see in the picture, and now that we have the concept of the infinite and the bioplastics, we have the mission or idea in this project is to establish circular and sustainable value chains for all the bioplastics that we will probably found in the future packaging, textile and agriculture waste streams. So we are talking about 3 value chains that will be packaging, textile and agriculture that will involve in the waste streams, they will involve the presence of bioplastics. We will organize the activities from the beginning of the end of life, that is that we are not starting in formulation of bioplastics, we are starting in the collection, sorting, and we will stop in the recycling techniques because we are going to try to give the more efficient techniques to each one of the waste streams, and the further upcycling that will be producing add-value products. So the idea of Moebius is to combine the expected growth of bioplastics in this near future, and to provide the market end-of-life solutions for these bioplastics. Well, we are, as Chiara commented, we are a Horizon 2020 project. We are a project funded by the CBE, Circular Bio-Based Europe organization. And the general object of this project is demonstrating the integration of this bioplastic, this end of life, into 3 value chains. As I have already commented, one of them is packaging, mostly located in Spain, textile, mostly located in Italy, and agriculture waste stream containing bioplastics, located in Germany. We are a consortium of 21 partners plus 2 affiliated entities led by ITENE, which is my research center. And as I have already commented, we are starting with a feedstock which is not quite normal because we are using a waste feedstock containing bioplastics. And the final outcome of the project will be to produce 3 upcycle demonstrators, 1 per value chain, from the end of life of these bioplastics waste streams. Of course, we will reduce waste. This is other of the objectives. We will decrease the environmental impact and provide a sustainable alternative to fossil resources. And we will create a novel model for the bios end of life because we think that this growing should be parallel to the generation of the solution for the final end of life of the bioplastics. How are we supposed to deal with this big challenge? This is you can find this in the poster in the bottom of the room, and yeah, we are organizing a transversal, in a vertical, horizontal, and transversal way. The horizontal way is each one of the value chains. You can see the packaging. Here we will deal with post-consumer packaging stream containing bioplastics.
Same thing for the agricultural waste stream, and post-consumer, again, textile waste stream. As you can see, we have also vertical activities related with the collection as the initial at the beginning of the project, the sorting, the treatment. We will stop a little bit on that, the upcycling, and the validation of the final demonstrators. For each one of these vertical activities, our methodology is that one RTO, a specialized RTO, will lead the activities in the low scale experiments, and this will be supported by a specific company that will upscale all the activity. I mean, for instance, for the collection part, and for the packaging waste stream, there will be a specialist RTO, which is, for instance, Titanic, that will support, and we will be supported by a specialized waste manager. This is the methodology that we are going to follow in each part of the vertical activities. Additionally, we are supported again by transversal, the so-called cross-cutting or transversal activities. They are the safe and sustainable by design principles. We will be supported as well by the LCA, LCC, and social LCA principles. And at the end, our idea is to collect the best practices for optimal treatment for each one of the value chains, for each one of the waste streams, and these best practices will be collected into a decision support system. That will be another outcome of the project. If we will, I will try to be brief because I know we have not much time on that. Okay, I take a breath. Okay, so yeah, if we make the zoom on the recycling processes, because this is the objective of today, yeah, we will start with the sorted material. That will be an additional challenge, but maybe in the next sessions we can discuss on that. But okay, we will have the sorted material for these 3 value chains, and of course we will have to design a specific pretreatment in order to go for the recycling. Here in this project, we are going to work on 4 types of recycling. That is the mechanical or physical recycling, chemical recycling, biorecycling, and thermochemical recycling. As you can see, we have put this kind of triangle upside down because we want to transmit here that we are going to prioritize specific techniques that are optimizing each one of the streams. I mean, we are not going to put too much effort in the recycling chemically polymer or a blend of polymers if it is possible to do it by means of mechanical or physical techniques. So this is part of the best practices and the support decision tool that we are going to design here. Again, I want to emphasize that each one of these techniques, these boxes, are led by a specialized RTO for the low TRL activities, and a specialized partner will be in charge of the high TRL or the big size activities, the upscaling, I mean. And we will support it again by the support decision tool, sustainable by design principles, LCI, LCC, and social LCA. For the pretreatment, I have mentioned these activities yet, but yeah, we will try to meet with the requirements of the recycling processes. This will be a specific pretreatment for each one of these 4 kinds of recycling that we are going to do in this project. And yeah, we will produce condition residues. Regarding the mechanical and physical recycling, yeah, we will start with these conditioning residues, and we will have to meet the requirements in this case of the final demonstration. In this way, we will have to design a tailor-made treatment related with that will have to do with the specific characterization of this conditioning residue. we will have, of course, to deal with, we will have to design this extrusion or compounding methodology by means of additivation when necessary, or blend with virgin material, which is a common practice, at least in the conventional and not bioplastics. For the chemical recycling, this is what in the center of the slide you can see what was written when we were studying this project in the moment of we wrote the proposal, and these were the strategies that we had for each one of the candidates or the polymers and blends that we had in that moment. But this bioplastics market is a live market. So at this moment, we are trying to identify and to double check if all this work that we made in the past 1.5, more or less, year ago, we will have to validate if this is still valid for that. We will review the state of the art regarding this validation. We will try to reselect the specific route for each blend or each kind of bioplastic that we are dealing with. These routes will be chemical, biochemical, or thermochemical. This applies for those that are not able to be recycled mechanically, because we are applying here the hierarchy that I was mentioning before. And finally, we will verify the selected route by means of, again, two-stage experiments. Low TRL that will be done or performed by an RTO, and high TRL experiments that will be performed by a specialized company or partner within the consortium. Okay. This is an example of the innovation that we are aiming to do in this project. For instance, for PLA depolymerization, we are going to perform hydrolysis with selective catalyst, or alcoholysis with specific catalysts such as metallamides or deprotected solvents, but this is only an example. It is not already started yet. And similar things for PHB and PVAT that we are expected to find in these waste streams. We are talking here about methanolysis and hydrolysis again. And I stopped with the chemical, and I jump to the biorecycling, which is also one of the parts of this project. Here we have again two steps, and two steps within each one of these steps. I mean, first thing will be to select the enzymes that are potentially degrades the selected bioplastics. These enzymes should be manufactured and upscaled, and after that, we will have to develop the enzymatic depolymerization at low scale and at high scale. So again, two steps upside and two steps in the part below, and of course the downstream processes for monomer and oligomer recuperation is also a part of this biorecycling part. And finally, for those streams that are not able to be treated either by mechanical, chemical, or biochemical processes, we are aiming to design a specific gasification process. I want to emphasize that it is towards the zero waste, and this gasification process will be designed in order to produce an enhanced syngas compositions to be used as a commodity for the chemical industry, or for instance, the production of methanol or hydrogen. So I think it's all from my side. I did it as quick as possible. And I'm glad to be here again. Thank you. And I'm happy to hear what my colleagues from similar projects are going to share with us. Thank you.
Good afternoon and good evening. My name is Jan Pels. I am not the coordinator. Kevin O'Connor is the coordinator of Rebiocycle project. And he's giving a presentation very similar to this one, but somewhere else in Europe. So he asked me to be his replacement. I am the leader of the Dutch hub and the leader of Work Package 3, and I hope to tell you everything, but my speech will be biased towards these two things, the Dutch hub and Work Package 3. The reason for this project to exist or to be proposed was to do the upscaling of the recycling technologies for biodegradable plastics. So not necessarily for bio-based plastics, but for biodegradable plastics. And upscale that from the laboratory, where everybody has more or less done what is possible, to pilot scale. That's the motivation, that's the objective, that's the strategy. And while doing this, we create data and information, and the information should lead to a portfolio that everybody, and that includes the recycling industry, but also the brand owners who are supposed to do the transition towards biodegradable materials, the policymakers and the general public, that we have data to show them or to convince them. We do this in 3 hubs. This is an unusual way to deal with European projects because we want to integrate, but within the 3 hubs are actually groups of companies and institutes that already work together, and they have all their own specific focus, but there are overlaps and integrations. I'll give you a more complex table later on where these overlaps are. But there are 3 hubs: the Dutch hub, the Spanish hub, and the Italian hub. And well, Torwas, Eimplaats, and Novamont are leading those. And there is in the Spanish hub also a big Irish representation. That's where Kevin O'Connor comes from. Besides these hubs, there are horizontal partners, and they are the ones that evaluate what's made in the Dutch hub or in each of the hubs. We will make recycled bioplastics, recycled biodegradable plastics, and Arapaha and Sulapak will evaluate what we make, and the others are hopefully compiling all the data that is coming from us. So EU Bioplastics and ARCA have a lot of work to do, but at the end of the project. Okay. So I mentioned already that we are taking this to a portfolio. We want to have slides or demonstrations that it can be done. We can do recycling of biodegradable plastics. We do this in hubs, not only because it grew that way, but also we will be dealing with tons and tons of plastic waste, and transporting waste across international borders is not easy. If it's a sample of a few kilograms, well, of course you can sneak it in the train or in the booth of your car, but if it is a truck or 2 or 3, then you need licenses, permits, etc. So it's not easy to cross the border with waste. And recycled plastic is waste. So some key numbers, you can look them up later. It's one of the 3 projects. The approach within each hub is to do 3 steps. First, we of course will do gathering the materials and do sorting. And we will focus on PLA, PHA, and composites. And the composites are also known as a mater B, the material that Novamont makes. And well, in the Dutch hub, we tend to think that sorting is really easy. And in the Italian hub, they say, well, it's quite complex. And this illustrates exactly what this project is about. Get data, get the real one, not opinions, not experience, but data. Is it possible? How can we do it? What does it cost to sort out tons and tons of PLA? We don't know. We think well, I've seen the machine is working, but now 10 tons of waste plastic, 1 ton of PLA. Well, let's try it. Let's see. Let's get real data in real machines, big machines. Then there's the recycling. The recycling is done through mechanical, chemical, and biological ways. And the mechanical ways is, of course, grinding it up, milling it, making new granulates, and reuse the polymers as polymers. And in the chemical recycling, we go back to the building blocks, the monomers, and from there, we will recycle them into the stream where the lactic acid and the other original materials, the feedstock of the bacteria, and that's only in the biological ways, are used. So in the end, those recycled PLA and PHA and recycled composites cannot be distinguished from the original one. The only tricky thing is they have a waste status. So we need somewhere an end of waste thing. That's in for finding out by the horizontal partners how to do that. Of course, we will make then kilograms or maybe tons or maybe hundreds of kilograms of recycled materials. And those will be evaluated because I just said, and you maybe believe me or not, that the RPLA is exactly the same as a PLA, but is it? That has to be verified. And not on a gram scale, but on a kilogram or a 10 or 100 kilogram scale. Can we actually really make the same objects that originally were made from virgin PLA? That's the question. We hope to solve it. Well, three materials of all of the dozens that exist. 4 technologies, 3 hubs that made too many combinations even for the European Union to fund. So within each hub, we focus. The Dutch hub focuses on PLA and PHA and chemical recycling and biological recycling. We make juice from lactic acid and other acids and feed it either to a chemical plant or to bacteria. The Italian hub focuses on the composites and on the chemical recycling of that. And the Spanish hub will do a bit of everything, but mostly PLA and PHA and the mechanical recycling and biological, not chemical. So that's the axis. The O's are the interactions. Because of the juice that we make in the Dutch hub, we will send samples to the Spanish hub so that they, in their bacteria, can demonstrate, do we have the same results? And if we have time and money left, we will get some of the composites from Italy shipped across the border. Yes, that's a trick. And put them in our machine, in our chemical recycling, and see what happens. Can we do this? Or is their way of chemical recycling a lot different from ours? And get data. Well, I want a truck full of this stuff, not a kilogram. Okay. Now it's 7 minutes left. Okay, that's easy. This is how the recycles in the Dutch hub are done. It all starts with PLA objects, and I have a few with me at the table. You can see and hold them. They are supplied by Total Energies Corbion, who is present here and who will have a stand in the conference. They bring 500 kilograms of objects. Yes, you do. That goes mixed in with 10 tons of other plastics to a site of the NTCP, the National Test Center for Plastics, and they will sort it out. And of the sorted material that will be going to Torwash, to our company, we will build a pilot installation that we put on the parking lot of NTCP and feed whatever is sorted out. We make juice, liquor, lactic acid concentrate that goes to Corbion. Corbion is one of the mother companies of Total Energies Corbion. They will upgrade it and assess the quality and make the lactic acid that goes then back to Total Energies Corbion, and they will really make new RPLA from it. And I know they can. They've done it already in Thailand. And now I want to have it done from the waste stuff. Well, they make granulate that goes to Arapaha. They will turn it into the objects they make, and the Arapaha will assess it. And so we're back to PLA objects. This is the circle for PLA. There's a similar circle for PHA. They come from Kaneka. Also, Kaneka is here present, and they will be at the stand. They will also deliver to us 500 kilogram of materials. It's not yet in their warehouse, but we're discussing this. It goes to sorting, it goes to Torwash, it goes to liquor, and that liquor does not go to Corbion, but goes to Pax Biomaterials, also present here as a stand. and they will grow their bacteria, and we will reroute some of it to the Spanish hub so that they can grow their bacteria. They make granulate that goes to Sulapac makes objects, and so we close the circle. We want data of how this circle is closed and how it's difficult and where are the challenges. This is a slide of where we are actually located. So the Dutch hub is quite big, but the biggest distance between 1 and 2 is about 100 kilometers. So Italian hub is a bit bigger, but it's still all within the Netherlands. Now, I have a few minutes left to do some promotion of Torwash and to explain Torwash to you. Torwash is a small company, a spin-off company from TNO, and we do the upscaling of the hydrothermal treatment of biomass, and in this case of PLA and PHA. And then we return it to the original building blocks, to the monomers. And in doing this, we can separate it from the blends. The question was really correct. No plastic is pure, none of it. We always have mixtures, blends, but we can get out lactic acid from mixes. And every of these polyesters and polyamides has different conditions where the optimization of the hydrolysis is. And polyethylene, polypropylene, and addition polymers do nothing. Well, if we make a plastic from a bottle from PLA and a PET wrapper and a polyethylene cap, we can separate them. The PLA dissolves and goes into solution. The wrapper shrinks and sinks, and the polyethylene melts, floats, and when cooled, solidifies, and that's how we can separate them. We would like to have this done with many others, and I'm talking with brand owners and the manufacturers of stuff, and to convince them that now we are designing these biodegradable products. This is the moment to implement the recycling of the design of these things at the start. We should not wait until they are there and on the market. And then the marketing people have already decided what's good for us. And there are maybe ways to do it. And I can show two examples, but I don't have the time to do that. Yes. But I really want to emphasize that the design for recycling is key to the success and to the growth of the use of the recycling of biodegradable plastics. And this does not only apply to Torwash, but to everybody of us. So this is the thing, what we will make. Actually, this is the mobile Torwash installation that we made for sludge. We will make one very similar in a mobile container and move them around. It will be, the key will be, the core is in a 1 cubic meter batch reactor. And it's not the full scale. It's the full scale is not going to process 1 ton per day, but 5 tons per hour. That's what we aim for. That's what you need for a real big and economically viable recycling of PLA to lactic acid. But there is not that much lactic acid. It simply does not exist yet. So I hope that the predictions of EU Bioplastics and Nova Institute will come true, that by the time it's 2032, there will be a lot more and lots of more PLA and PHA used. And that's why we also do not do work on PBAT, PBS, and all the smaller ones. If they grow, if they come back, yes, we will find a way to do it. At the moment, they're just an interference and contamination. So, in the last minute, getting waste from mixed plastic is the most difficult to do. So we would start not with collecting waste from the yellow bin and or the orange bin, but with closed loop systems where that fits more to the scale of the units that we have or that we will have. And these are examples, and I will discuss this at the table. But for instance, the cups from Happy Cup, at the end of the festival, they are collected, they're washed, and the ones that are broken cannot be used. But they are collected, and in a closed loop system. They have already been pre-washed. We can take them. And that's much easier than getting one from the recycling companies. So challenge is enough. And I would like to keep those for the discussion at the table. Thank you very much.
All right. Thank you. Good afternoon. And also thanks to Chiara that even though we're not invited you for a consortium, we're still allowed to present here. So I'm presenting actually the final sibling of these three projects that just started a couple of months ago. And this one is Prosper. And I think parts of the things I will share will look similar as to the presenters before me because we applied to the same call, but I already spotted quite some nuances and differences that actually will show and demonstrate that these projects will probably go hand in hand in tackling this enormous problem or enormous issue that we have. So my name is Wouter Post, by the way. I'm also not coordinating this project, but I'm from Wageningen University and Research. A little bit more on that later. But first, introduction to the Prosper project. So our project, the motto of the project is to close the loop, make bio-based plastics circular. And then what we will do, actually, we'll demonstrate the techno-economic feasibility of sorting and recycling of bio-based plastics in 4 different actual waste sorting plants located in Spain, France, and Italy. More on that later. And we focus on packaging. So packaging from the recycled bio-based plastics. We start in September. And we will run till August 2028. And that's what we'll look at. And if you see who are partners, then you see probably on this list, well, some names that are familiar to most of you, maybe also some new names. I don't have the time, I think, to go through them all, so I won't. But I would like to highlight that Ghent University is actually the coordinator, and Steven de Meester is actually the scientific coordinator of this project. A big expert on recycling. He couldn't make it, so he asked me to take his place. I'm from Wageningen University and Research, and I'll take the opportunity to briefly introduce, our institute to you all. So, what we do, we're part of Wageningen University and Research, which is part university and part research institute. I am from the Research Institute in Wageningen, and we're actually a contract research organization with governments, NGOs, institutional funders, industrial companies, all as our partners. And we work on transition towards a more sustainable future. And in the case of my team, on towards more sustainable use of plastics. Got a team of about 30 highly engaged experts all working on plastics. You can see where they are working at. This is our facilities where we show, bring academic developments towards, industrial application. That's where our focus is at. Now, type of work we do. So we work, actually, our philosophy is to design both for functionality and end of life. End of life depends very much also on the functionality, but also where this product is ending. So you could envision 2 lines of our research, one being from waste plastics via sorting and mechanical recycling to granulates and products, which is very much linked to the work we're going to do in Prosper. But we also look at the development of making new biodegradable compounds, show that they can be processed into products, but also show that they, in the specific end-of-life environment, biodegrade in the time frame that we want them to. So that's what we do in Wageningen. Now, then more on the Prosper, and actually what's the vision that lies under Prosper. And I think there's 2 elements in which Prosper is actually built. One is the statement that plastic waste does not get plastic waste that does not get sorted will not be recycled, and plastic products without scale will not get sorted. So those elements make actually how this project is built. And you already see the word sorted in there twice, and that's actually one of the focus points of this project. Now, what is the philosophy of this project? Is actually that different sorting plants in a certain region, call it a hub, will all collect their bio-based plastics and send them to a central sorting refinery, which you could say the new bio-based sorting refinery. And the idea is that in this way you create scale, and you don't have to, not every sorter has to install separate equipment to make their business feasible, because that's the problem at the moment. You don't They don't have the monetary funds to make these small streams feasible, but by in such a way you can create scale. And ultimately, this new bio-based sorting refinery can then make separate streams, PLA recycling, for example, PBAT recycling, PHA recycling, but can also deal with specific blends that were already mentioned. And in this project, they will actually play quite a crucial role. But what's interesting in this concept is that actually we're not solving the bio-based or the bioplastic recycling issue, but we're actually looking at small waste fractions of plastic. So in that sense, we can even maybe in this concept team up with some, unexpected friends that are also small, be not bio-based, be not biodegradable, but have the same problem. So I added here polystyrene recycling with a big question mark, because we still have to figure it out. It's also not in the official call text, but it is something in the consortium where we're thinking about, because this is actually in a way a polymer that has exactly the same problem as the polymers that we are all working here on. And maybe we can team up. So how are we going to do that? We look at waste. We actually start from waste, and we're going to get that from different places in Europe. And I underline the complications that it will bring in transporting waste, but we have partners in there to solve that. We have to characterize this waste. So there's a whole bunch of partners who are fully loaded and experted at that. And then we have different levels of sorting. And I think this is where the heart of our project lies. Unfortunately, I'm not involved in that, so don't ask me too many difficult questions on that. But this is, I think, one of the main elements in the project, and we will develop new, near-based systems or also artificially trained systems to, get this sorting in an effective way. And then the sorting will move to the pre-treatment for the two recycling streams that are central in this project, one being on mechanical recycling and the other one for chemical recycling. And these will be recycled. So the feasibility on an industrial scale, can we recycle these, different materials via these ways, ultimately yielding three different products, being, film-based materials, bottles and trays made from PLA, and also bags produced, based on Novamont feedstock. This project, divided in several work packages, as any project. So you will see here work package 1, 2, and 3, 1 being on characterization sorting, 2 being on recycling, and 3 is actually the investigation of the properties and how to develop products. They are all being performed on, from lab to near industrial, and then all move to work package 5, where we'll demonstrate these technologies on a, industrial relevant level. The project is also accompanied, of course, by a couple of supporting work packages. So work package 4 will look at circularity, safety, and sustainability, whereas work package 6 will look at the market uptake and how the waste management infrastructure will look like. And we also will do, of course, a lot of dissemination communication, and so that Gent will manage the project from work package 8. Maybe more interesting are the 3 different recycling pilots we're planning. So we have an Italian pilot, which is mainly pulled by A2A and Novamont, a Spanish pilot, which will be managed by FCCMA, and where GCR, it says here Envico, but GCR is actually their new name, will play a massive role in developing new compounds and granulates that can be, used for new products. And in France, the French pilot will take place, which will be managed by Suez, and they will link closely with Futero, which kind of makes that this is a PLA-focused pilot plant, which focuses both on the mechanical and chemical recycling of PLA. Now, to wrap up, this project, what we will do, and what we will build on, it's actually, we build on the fact that due to these relative small volumes that we currently have in bio-based plastics, they are not being recycled, which blocks their scale up. So this project, Prosper, will aim to think out of the box and find a way to get, these bioplastics out of this catch-22, which we all know they are in. Now, I think we have a strong consortium along the whole value chain, so we are fully suited to tackle the complex problems that are ahead of us. And I would like to underline again, I think it is not only solving the bioplastic recycling issue, but we're actually dealing with the question how to set up a cost-competitive sorting and recycling scheme for minor polymer fractions. And maybe there we can make some unexpected friends. Now, we truly believe, and I don't think anybody in the room would fully disagree, that bio-based and biodegradable plastics all have the potential to be circular. And we will demonstrate this at an initial scale in 3 EU pilots focusing on sorting, recycling, and reuse in new plastic products. So I hope this gives a bit of an overview of our project. And if there's time, I can take a couple of questions.
Good evening, everyone. I am Chrysanta Argiti from Agricultural University of Athens, and currently I'm pursuing my PhD studies in the group of Bioprocess Engineering and Circular Bioeconomy. And today I would like to give you an overview on the pretreatment of packaging waste using plasma technology. So to begin with, I would like to give you a better understanding of the main research interest of our group, which is mainly focused on the development of novel biorefineries, microbial fermentations, and circular bioconversions. We aim to valorize agro-industrial waste and food waste to derive value-added products and use them as feedstock in microbial fermentations for the production of chemicals and bioplastics. Currently, we're also working on the development of upcycling processes of biopolymers as an end-of-life use for the production of new biopolymers. To upgrade conventional biorefineries, we integrate novel electrification technologies such as the in situ production and extraction of organic acids using electrochemical membrane reactors and non-thermal plasma technology at the pre- and post-treatment stages. Having said that, BioSurpack project is a European Horizon project which stands for the production of PHAs from broomstick grains by integrating plasma technology into value chain and the enzymatic recirculation of post-consumer PHB-based packaging. So the produced hydrolysate is used in microbial fermentations as a carbon source for the production of PHB and targeting to high packaging performance for food and cosmetic applications. Also, plasma discharges can be used for both coatings, functionalization, and depolymerization of polymers regarding depending on the intensity of the discharges. So BioSurpack is mainly focused on the enzymatic recirculation of post-consumer bioplastics by applying advanced oxidative processes like plasma technology for the partial depolymerization and the enzymatic recirculation for the production of plastic monomers. The produced hydrolysate is then introduced as feedstock for the production of new PHB. This slide aims to highlight the major problem of the plastic waste management. Currently, only the 70% of the total plastics produced are properly recycling, while the majority end up in landfills, followed by incineration, resulting in the production of microplastics and greenhouse gases emissions. A solution to this problem is to produce mechanical recycled by design plastics, reducing this way at around 1 to 2.7 CO2, the CO2 emissions per ton of polymer produced, but we still have the problem of the production of microplastics, and these plastics end up to landfills. So coupled with the high energy demanding and CO2 emissions during the production stage, this underscores the need of new alternatives such as bioplastics with circular end-of-life scenarios. At this point, I would like to introduce you to the principles of non-thermal plasma technology, refers to the fourth state of matter. Plasma is generated when a gas is exposed to an electrical field, resulting to its ionization. So this advanced oxidative process operates at ambient temperature and pressures, eliminating the use of chemicals and solvents. Thus, by depending solely on renewable electricity, we can achieve improved resource and energy efficiencies, and plasma can stand as a pretreatment method for the achieving high carbon removal efficiencies.
So this slide, you can see how a plasma-based biorefinery of Brisbane grains for PHB production can significantly improve the sustainability profile of the whole process. As you can see here, when we used plasma technology in the stage of the pretreatment, we achieved a 50 to 60% reduction on the total on the global warming potential, which is expressed to the CO2 kilograms of CO2 that are produced per kilogram of produced PHB. Thus, we have a significant reduction on the abiotic depletion by around the half. The key innovation here lies in using integrating electrified technologies into biorefineries and depending solely on renewable electricity. And by this way, we can achieve a significantly improvement of the total of the carbon removal. Regarding the recirculation of consumer bioplastics, an end-of-life scenario should rely on the chemical and enzymatic recycling of bioplastics. This way, we can introduce new ways to transform waste into valuable resources. Here is an example of the alkaline degradation of PHB using sodium hydroxide solutions and the thermal degradation of PHB. In both cases, two monomers of the two monomers, 3-hydroxybutyric acid and crotonic acid, were produced. And in the case of the alkaline degradation, we have a higher production of crotonic acid. We observed then that when we use these hydrolysates in microbial fermentation as carbon sources, at the higher concentrations of the hydrolysate, there was an inhibitory effect in the bacterial growth and production of PHB due to the presence of the crotonic acid. In this slide, you can see a schematic representation of the mechanisms of plasma-induced plastic degradation. The process begins when the surface of the polymer is exposed to a chemical-rich environment consisting of nitrogen and oxygen reactive species. And by this way, by optimizing parameters such as electrical discharges, the gas type that we use in the plasma, and treatment duration, we can selectively modify the properties of the polymer and induce surface roughness and partial fragmentation of the chains. By this way, we can achieve, we can increase the hydrophilicity of the polymer, make it more easier for the lower molecular weight fragments to be easily accessed by the enzymes. 7 more minutes. Oh, that's fine. Okay. Regarding the pretreatment of the of PHB samples, we employed a plate-to-plate plasma reactor, and we evaluated the different moisture contents into the sample. So the hydrolysis, the degradation efficiency of PHB was evaluated regarding the reduction of the molecular weight of the pretreatment samples. And we observed that the higher the moisture content, the lower the molecular weight of the pretreatment samples. So, this is also reflected to the enzymatic degradation of the PHB samples, and maybe this is attributed to the better dissolution and the more efficient mass transfer of the reactive species into the water, and especially the ozone and hydroxyl radicals, which are responsible for the oxidation of the polymer surface. And the next set of experiments, we carried out an indirect plasma pretreatment using plasma-generated nitric acid, which was generated using a microbubble reactor. I have a video here, but I don't know. Okay, you can't see this, but this is the reactor, and we can see how the plasma is generated and excited through microbubbles, which allows the homogeneous dispersion of the reactive species into the water. So the nitrogen oxides are generated in the gas phase, and then they are subsequently dissolved into the water, reacting with the oxygen species and producing nitrous and nitric acid. So here we carried out some experiments using different concentrations of nitric acid solutions from 0.5 to 5%, and at various temperatures from 70 Celsius degrees to 120. And the results showed that the higher the temperature, in combination with higher nitric acid concentrations, the lower the molecular weight of the pretreated PHB samples. In this case, we used PHB pellets for the pretreatment, and we observed that regarding the enzymatic hydrolysis of the samples, there was a reduction to the selectivity of the enzymes due to the presence of other components like additives or stabilizers. So, regarding the strategy for sustainability, calls for the transition to a safe and sustainable by design approach for polymers production. One of the main challenges and the current toolboxes is the segregated LCA of bio-based processes, which leads to conflicted assessment results and generate confusion to policy makers. So to incorporate safety and sustainability key indicators during the upcycling processes, new models to be developed in order to evaluate the LCA of the material prior to its production, and taking into consideration the demanding of developing circular end-of-life scenarios, European Alliance of Raw Materials should reassess the assessment, reassess the framework, and introduce new feedstock as resources. Regarding the disposal stage and aiming to eliminate the mismanagement, new analytical tools and novel processing technologies to be developed in order to achieve an efficient quantification and separation of additives into the plastic waste. And thank you very much for your attention.
Well, good afternoon, everyone. My name is Ronnie Salcedo. I am project manager at Diversia, and we are task leader in the Biomac project respecting to the food packaging test case. As we grapple with the pressing issue of plastic pollution, bioplastics and compostable materials have emerged as a promising solution for the industry. These materials are often offer a more sustainable approach, also not only to the packaging industry, but also to other industrial applications. However, to fully realize if these materials are provide environmental benefits, we must address first challenges associated to the development of bioplastic and also to their recyclability. Biomac project, it's a groundbreaking initiative aimed at developing innovative solutions for bioplastic and also their recyclability and the process. It brings together a huge consortium of around 33 entities composed by leading academic institutions, also research centers, and industrial partners, all together addressing critical challenges for the bioplastic industry. Biomac primary objectives are threshold. The first one, it's technological investment. The project is dedicated to developing cutting-edge technologies related to the development of bioplastic with different nanomaterials, and also to the recycling and the process as well. Also, this project is dedicated to technologies such as chemical recycling and pyrolysis. The second main objective is the circular economy promotion. Biomac itself promotes a circular economy model by minimizing waste generation throughout the nanomaterial extraction process. This approach reduces reliance on virgin materials and also minimize the environmental impact related and associated with the traditional linear production business models. And the last, but not the least, is the environmental sustainability. The project focuses on developing eco-friendly methods to minimize energy consumption, greenhouse emissions, and also the generation of hazardous wastes. While achieving this objective, Biomac is committed to develop demonstrators with bioplastics for 5 specific industrial applications, which are automotive application, agricultural, food packaging, construction, and also printed electronics. 3 of them are also ready. You can find public deliverables already published on our website. At least for the automotive, printed electronics, and agriculture, they are ready. Food packaging results will come by the end of this year. And for the construction, we'll have to wait until February next year. In order to leverage from Biomac, MAUE, BIOS, Recycle, BioSubpack that are present here in this table, benefits, we first need to understand what is the current situation of the recycling of bioplastic in the industry. According to the European Environment Agency, Europe overall recycling rate is around 46%. And if we see the figures, particularly to the food packaging applications, the figures goes up until 64%. Of course, we are talking about virgin plastics. I mean, recycling conventional plastics. I bet that if we go for bioplastics, these figures are lower. But even with these rates, the recycling industry is facing challenges, such as limited recycling infrastructure, the existing infrastructure for recycling virgin or bioplastics is often inadequate, with many facilities lacking with a lot of equipment and also processes to handle bioplastics itself. This limitation hinders, in one side, the efficient collection, the sorting process, the recycling of bioplastic, and also hinders the widespread adoption. Sorting and identification challenges distinguishes between different types of bioplastic materials and also conventional plastic. It's a complex task. It is not the same processing post-industrial waste than processing post-consumer waste. Also, food contact and compostability, which is a specific challenge for the food packaging sector. It's a challenge because ensuring safety and hygiene of bioplastic for food contact, during the recycle process, it's crucial to prevent contaminations when they go back in the circular model. And then the economic viability, the recycling bioplastic often lags behind that of virgin materials. Factors such as the cost of collection, sorting, and processing, coupled with a lower market value of recycled materials, can make recycling less economic for the industrial participants. And now that we know challenges and the benefits of different projects, and also for the bioplastics, what industrial partners are doing in terms of sustainability. And that's where I come to talk about my numbers. Eversia has achieved a big milestone this year, and is that 80% of our production is certified as sustainable. Behind this achievement, there's a lot of work, effort, and also investment. Thanks to this, and together to our path throughout all our participation in different types of projects and initiatives around Europe, we provide to the market already recycled solutions, highly recyclable materials, and also biocompostable materials. And we believe that collaborating with different initiatives of the ones that I sit in this table today, we can reach the percentage required for the 100% of sustainability soon. All our experience within projects and also our experience in the market have shown us that there's still a long path to walk on, respecting technological and also at a political level. And I hope that some of the experts today here can agree with me, and also people attending tonight, it's that we still need to work and advance on sorting technologies. We need to invest in sorting technologies such as near infrared spectroscopy and machine learning also to improve the accuracy of sorting. We need also to explore new chemical recycling processes, because it's for bioplastic, recover valuable materials for complex bioplastic it's difficult yet. Also, we need to raise awareness and in educating our consumers about the importance of the proper way to dispose of this waste and also the recycling of bioplastic products. And at policy support and policy level, we can say that also we need investment in research and innovation from our policymakers. Subsidies and incentives are also important because it's not only on big players, this is also on SMEs and mid caps and also end consumers. And also we as industrial participants must work on the product design for recyclability and also to design new packaging and new materials for biodegradable with a biodegradable design. And we believe that addressing these challenges requires a collaborative effort involving industry partners, policymakers, stakeholders, and also consumers. And that's everything from my side. Thank you very much.
Randy. I think you have a nice summary here for the entire session. Thanks a lot. So we got here an overview of mostly, let's say, younger projects that just started, so they use a lot of future tense when they were presenting, and that's normal. But we also have two outstanding projects that are finalizing the activities. One thing that maybe I can just mention about the BioMac project is that the BioMac is creating an open innovation test bed. So it will, as soon as the funding is finishing from the Commission, they will set up pilot lines that users, so companies can use based on some fees, not enormous amounts, I saw, where you can actually use the pilot lines for testing products, testing polymers, testing, and using the labs that are existing, that have been funded for the past 5 years. So this is something that will give, let's say, a very long term activity also for the partners involved into the packaging, the automotive. So if you're part of this kind of sectors, you can also take advantage of the pilot lines and how they will build their own services in the next few years.